We're going to finish off our unit today by distinguishing between two different types of collisions. We can classify collisions in any one of a number of ways, right? Is it a T-bone collision, like a 90-degree intersection? Is it a glancing collision? Is it an explosion? We can classify them in any one of a number of ways, but the way we're going to classify them today is based on kinetic energy. We're going to define an elastic collision. Elastic collision is a collision in which momentum, well, momentum is always conserved, right? So that doesn't classify it. But it's a collision in which momentum and kinetic energy are conserved. Kinetic energy isn't always conserved. We always have energy conserved, but if we factor in all the types of energy, including thermal energy that is often lost in a collision, but kinetic energy is sometimes conserved. If it's an elastic collision, kinetic energy is conserved. Momentum is always conserved. Kinetic energy is sometimes conserved. In an inelastic collision, well, momentum is, of course, still conserved, but kinetic energy is not conserved. In other words, kinetic energy is lost. You're never going to gain kinetic energy. That's not true, actually. You can gain kinetic energy in something like an explosion. A bomb has zero kinetic energy before and lots of kinetic energy after, but we're not classifying explosions. We're classifying collisions. And in a collision, the kinetic energy will either stay the same if it's elastic, or it will be lost if it's inelastic. It shouldn't be gained. If you find the kinetic energy was gained in the collision, you've made a mistake. You should try again. Now, in a collision, a couple of different things can happen. We can have our two objects either stick together or they can bounce apart. If they stick together, it will, every single time, be inelastic. You will lose kinetic energy every single time. You won't lose momentum. If we take a look at the momentum immediately before and immediately after, the momentum will be the same. But you will lose kinetic energy. It will be inelastic if they stick together. If they bounce apart, it is likely still inelastic. So in other words, most collisions that we see are inelastic. But if they bounce apart, it could be elastic. It might be elastic. Well, how do you know for sure? If they stick together, we don't have to do any check. We know for sure that it's inelastic. We know that kinetic energy will be lost. If they bounce apart, it's probably still inelastic. We probably still lost kinetic energy. But how do we know for sure? Well, we calculate the kinetic energy before and after. Simple as that. We don't have to do that if they stick together because we know that kinetic energy will be lost. But if they bounce apart, then we've got to do a little check. Okay, we calculate the kinetic energy before, we calculate the kinetic energy after, and then we compare the two. Because sticking together, it's inelastic. Because bouncing apart, it's probably inelastic. Here's what I want you to remember. If in doubt, you're not sure, you can't remember how to calculate the kinetic energy to determine whether it's inelastic or elastic, or you're just getting inconsistent numbers. You're trying it a couple of different ways and you're getting numbers that don't agree with each other. If in doubt, go inelastic. Because most times it is. I would say 90% of the time it's probably inelastic. So if you're not sure, guess inelastic. And 90% of the time you're going to be right. Okay? 10% of the time you won't. Hopefully you don't have to guess. But because the collisions are usually inelastic, you're usually relatively safe. Now, there are certain times when we get truly elastic collisions, but it's very rare. Let me tell you situations where we're more likely to see elastic collisions. Okay, if I bounce a basketball against the ground, that's almost certainly going to be inelastic. If two cars collide with each other, even if they bounce apart, it's almost certainly going to be inelastic. If I have two billiard balls or two pool balls or two marbles hitting each other, and they bounce apart, that has a decent chance of being elastic, or at least very, very close. Reason being, when two very hard things like pool balls hit each other and bounce apart, you don't get very much compression or deforming of the pool balls, right? When a basketball hits the ground, the basketball deforms. When two cars hit each other, the two cars deform. But when two pool balls hit each other, they don't really deform very much, right? In Science 10, you learn that every time you convert energy from one type to another, you lose a little bit. Remember that? Every time you convert energy from one type to another, you lose a little bit. Okay, if a basketball hits the ground and the basketball compresses, then you're converting kinetic energy to elastic potential. And then when it bounces back, it converts the elastic potential back to kinetic. There's two conversions that took place, and in both of those conversions, we lost energy. So you can't have as much as you started with, right? But if two pool balls hit each other and they don't compress, then there's no conversion taking place. Kinetic energy remains kinetic energy. Because you haven't converted any, you're not going to lose any. Does that make sense? The only time you have truly elastic, like to an infinite number of significant figures, elastic, is when you have subatomic particles. Like two electrons hit each other and bounce off of each other. Why would that be completely elastic? No, like to a million significant figures, no kinetic energy lost? Well, if you have subatomic particles, particles that are as small as they can possibly be, how do they squish? How do they compress? Right? Even pool balls compress a little bit when they hit. There's a little bit of energy conversion. But when two electrons hit each other, or two subatomic particles hit each other, there can be no squishing. No energy conversion means it's going to be elastic. Make sense? If in doubt, though, 90% of the time it's inelastic. If in doubt, go with inelastic. But hey, in the end, you're usually able to calculate the kinetic energy both before and after to determine mathematically whether it's elastic or inelastic. Example number 1 says a 2,000 kilogram truck traveling north collides with a 1,500 kilogram truck traveling south at 12 meters per second. They stick together and they head off at 6.28 meters per second after the collision. Is it elastic or inelastic? And then how do you know? Well, there's a quick answer to this question. A very quick answer to this question. Is it elastic or inelastic? It's inelastic. And how do you know that? They stick together. I'm going to justify that mathematically for you, but if you got this question on a test, you wouldn't have to go through the math on this question. Okay? Because you know when they stick together, it is 100% inelastic. I'm just going to show you how I would do the math here. I'm going to say EKI equals 1/2 M1 V1I squared plus 1/2 M2 V2I squared. Notice I'm not setting EKI equal to EKF. Don't do this. Like that's what you're trying to find. Are they equal? Like, well, we know they're not equal. But even if we don't know, we're not going to assume they're equal. Just calculate EKI separately. I got 1/2 of 2,000. By the way, notice I didn't circle anything in red here. Why did I not bother circling the north and south in red? Kinetic energy is a scalar. Okay, in the context of kinetic energy, elastic, inelastic, I don't care whether it's north or south. 1/2 of 2,000 times 20 squared plus 1/2 of 1,500 times 12 squared gives me 5.1 times 10 to the 5 joules. To 2 digits, right? To 2 digits, 5.1 times 10 to the 5 joules. There's my initial kinetic energy. My final kinetic energy is 1/2 of the total mass times VF squared, 1/2 of 3,500 times 6.28 squared equals 6.9 times 10 to the 4. Kinetic energy was lost. It's inelastic. Right? We knew that because they stuck together. But just a second justification that it's going to be inelastic. Since EKI is greater than EKF, it is inelastic. Again, this question, because they stick together, you wouldn't have to go through the math on this, but this is how you do go through the math if you're not sure. Example number 2 says a 5 kilogram ball traveling east collides with a 6 kilogram stationary ball. Immediately after the collision, the lighter ball travels north of east, the heavier one travels south of east, elastic or inelastic. If I had to guess on this one, what would I guess? I'd guess inelastic. Because most times it's inelastic, right? But we don't really know for sure on this one, whether it's elastic or inelastic. We've got to do the calculation here, right? I'm not going to bother circling things in red. I'm not even going to bother drawing a picture for this one. How come? It's a scalar. Do I need to do x and y components? Absolutely not. If I was dealing with this data in terms of momentum, then yeah, x and y. But for kinetic energy, I don't have to worry about that. I'm just going to say EKI is equal to 1/2 m1 v1I squared plus 1/2 m2 v2I squared. By the way, that's 0, isn't it? Because it's at rest, stationary. M1 is 5, 0.98. Gives me 2 digits, rounded to 2 digits, right? 2.4 joules. Separately now, EKF is equal to 1/2 m1 v1f squared plus 1/2 m2 v2f squared. See what I've done there? Like where did that 50 degrees north of east go? I don't care about it, right? I'm talking about kinetic energy. Kinetic energy is a scalar. That doesn't mean that all the stuff we've done up till now, the angle doesn't matter anymore. It does. Like for momentum, the angle always matters. X and Y always matter. But for kinetic energy, they don't, because kinetic energy is a scalar. Calculate this, guys, to 2 digits. It works out to be 2.1 joules. Hey, it's close. Elastic or inelastic? Inelastic. We guessed it was going to be inelastic because it is most times. But again, since EKI is greater than EKF, it's got to be inelastic. Yeah, I got a question for you though. If I rounded these to 1 digit, 2 joules, would we now say it was elastic?
No.
Well, why should I not round it to 1 digit? Like we're given 2 digits here, right? Right? Now, if this said 6 kilograms and this said, well, even if that just said 6 kilograms, okay, let's say this said 5 as well. My final answer in both cases should be rounded to 1 digit. And what would I conclude then? To 1 digit, I would say that it is elastic because they would both be the same number to 1 digit. Make sense? Is that hard? It's kind of a nice way to finish off because it's probably one of the easiest things we do in this unit, I think, right? You just got to remember to not pay attention to positives and negatives and not pay attention to angles and x and y components. Kind of like it almost goes against everything we've said in this unit, but it doesn't really, because everything we've done in this unit till now has been with vectors, and this is a scalar. All right?